or not? Not good, right? What's happening here? Well, I mean, look, if you get close in here, I think they're kind of indistinguishable at this point, right? So we didn't do a great job, but we didn't do a terrible job. Like, it does match in there, right? Like, it's just the further away you get, the worse it gets, right? Well, that's because I used a quadratic. How do you think I could get a better approximation? Increase the power. Why don't we do a cubic function instead? Third degree polynomial. Could you still follow this same process? Shouldn't you be able to get numbers for each one, right? And then if that's not good enough, let's go to fourth degree. Could we do it? Fifth degree. Could we do it? Sixth degree, 10th degree, 100th degree, millionth degree. Yeah? What about a polynomial that goes forever? An infinite polynomial. If we can do that somehow, what we would do is we would create a new representation for e to the x. This infinite polynomial would actually be what e to the x is. Now, if you don't believe me, I'm going to show it to you, all right? I'm going to show you, where we got here. Are y'all getting this? Like, I'm kind of trying to construct a new function out of an old function. And again, you're going to sit there and go, why are you doing this? Like, let me see here. There it is. A little too big. Okay, here it comes. All right, here's e to the x, right? I'm going to approximate it right now. Where is it? What the hell? Where is it? Hold on, I got to evaluate this again. Something's going on. There it is. I don't know what was happening. Okay. So right now, what I'm doing is I'm approximating e to the x with a constant function. So I started out here with a parabola, right? But what if we just started out with, hey, let's just try and approximate it with a constant function? That would be a shitty approximation, right? But at least they go through the same point, right? At the origin right here. I mean, not the origin. At 0, they both at least go through 1. That's not a very good approximation. Okay, let me go to a line. Okay, 1 plus x. At least they go through that same point, and they actually look like they have a better slope, right? Like it's closer. And then I could go to a quadratic. Okay, that's the one we just did. That's the one we just did, right? That's the quadratic. Now, what I'm doing, these dotted lines, is me leaving a trace of what was before. This was the line before. Now, the black one is our parabola, right? Now, let me go to a cubic function. Better or no? A little bit, right? Let me go to fourth degree. Better? Fifth degree, sixth degree, seventh degree, eighth degree, ninth degree. Do you see what's happening? I'm just kind of marching my way. See, it's still shitty out here, isn't it? But I can keep going and keep marching my way. Right now, we are looking at a 20th degree polynomial. That is a pretty good approximation of e to the x. Until you get out to about -8, then it's no good anymore, right? But I could keep doing this forever. And so I have an infinite polynomial, all right? Now, I'm way ahead of where we need to build a lot of structure before we can get to this, but the end result will be this. The end result will be this. We will show that e to the x, the function we've been dealing with our whole lives, can be rewritten as this infinite polynomial. 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x to the third plus 1 over 4 factorial x to the fourth plus 1 over 5 factorial x to the fifth plus ... forever and ever. Y'all know what factorial means? This means 2 times 1, this means 3 times 2 times 1, this means 4 times 3 times 2 times 1, 5 times 4 times 3 times 2 times 1, right? This is what e to the x really is, and it goes forever. Why is that useful? Well, because if I go to my calculator and I type into my calculator e squared, right? What does your calculator do? What does your calculator do when you type in e squared? You don't know, right? It just gives you an answer. What is it doing? It's taking 2 and it's plugging it in here, 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 here. Because this is just arithmetic, right? Can you square 2? Can you put 2 here? Yes. Can you square 2? Yes. Can you cube 2? Yes. Can you raise to the 4th power? Yes. Can your calculator do that? Yes. Can it do it fast? Yes. How far does it go? Well, whoever wrote the program has some predetermined condition on how far to go, all right? And if you change the setting on your calculator, you can tell your calculator, oh, I want more decimal places, right? So how far your calculator goes is going to say how far in this series it goes. Understand? This is what your calculator is programmed to understand e to the x is. What else is good about this? Not only does it make it useful for things like that, what if we wanted to integrate e to the negative x squared dx? That was the one I told you there's no method we have, right? We have no method for this. There's nothing we can do to find this antiderivative. But if e to the x is equal to that, then I can just kind of act like that's my x right here in the formula, and I can rewrite this as the integral of 1 plus, okay, now instead of x, I'm going to put what? Negative x squared plus 1 over 2 factorial, and then negative x squared squared, then plus 1 over 3 factorial, negative x squared cubed plus dot, dot, dot. Do you see all I've done is just use that formula and replaced all the x's with negative x squareds? Can you integrate this?
Yes.
Yeah, these are all just powers of x. That's all they are, right? Powers of x. Can you integrate powers of x? Absolutely. It's the easiest rule out of all of them, right? The power rule. You just add 1 to the power. You have to scale it, right? So I can do it term by term because there's pluses in between these. So I integrate that, 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 and I'll get a nice answer. Now my answer will be an infinite polynomial as well, right? So we're going to be, when we get to this, our answers are always going to be approximations. But in the real world, approximations are okay. Something you have to understand, like in the real world, even if you're manufacturing ball bearings for an aircraft, right? The tolerances on that have to be super precise, right? Well, this is an approximation because it goes forever and we can't go forever, right? But I can go as far as I need to go to be within the tolerances that you need, okay? So it's all right. I hope this gives you some sort of glimpse into where we're headed with this. Every function that is continuous, that you can kind of draw without picking up your pencil, every function out there can be approximated with an infinite polynomial. Every one of them. That means any function you've ever dealt with in your life, we can find some polynomial that's infinite that would represent that function, which means our calculators and computers can do something with those. All right? It's called the Weierstrass theorem. And it says that it's a proof that every function can be approximated as closely as you ever want with an infinite polynomial. All right. So now we'll get to that. All right, we'll get to that. Have I shown you that e to the x before? I feel like I showed you all that. No? Maybe. Maybe you'll remember it this way. If I write e to the x is equal to 1 plus x plus 1 over 2 x squared plus 1 over 3 factorial is 3 times 2 times 1 x cubed plus 1 over 4 factorial, 4 times 3 times 2 times 1 x to the 4th. This goes forever. Have I shown you this where I take the derivative of it? No? Take the derivative of this. What's the derivative of e to the x? Okay, it's self, right? What's derivative of that? What's derivative of 1? 0. What's derivative of x? What's derivative of this? X. What's derivative of this? So the 3 comes out, cancels, right? And so you get 1 over 2 times 1x squared, right? Plus, now here the 4 comes out, 1 cancels with the 4 down here, 1 over 3 times 2 times 1x cubed, right? Plus dot, dot, dot. This is that, right? That's that. E to the x is its own derivative, as this shows, right? That's pretty cool, right? What's the antiderivative, right? What's the antiderivative of e to the x? Itself, right? Okay, take the antiderivative of this. X. Take the antiderivative of that. 1/2 x squared, right? Plus, okay, take the antiderivative of that. I'm covering up the 1/2. 1/3 x cubed, but you have a half in front. So that's going to become 1 times 2 times 3, x to the 3rd, and I keep going, right? Antiderivative of that is 1/4 x to the 4th, but then I multiply it times this. So now I'm going to have 1 times 4 times 3 times 2 times 1, x to the 4th, plus dot, 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 right? Do you all see that this is this? Wait a minute, I'm missing something. I'm missing the 1, right? But remember, it's an antiderivative, so plus c, right? You have your constant. There it is. So I try to explain to my college algebra students, it's almost impossible to explain to them just how fabulous this function is. It is the only function that is its own derivative and its own antiderivative. There's no other one that does this. No other function behaves this way. And you can see it through the series that it works. Sorry, this is called the series, all right? All right, let's get to sequences. I'm done blabbing. Like I said, lots of definitions, so let's get through these. And we're going to do some exercises today. We're going to be fun, I hope. How are we doing on time? Halfway. All right, sequences. Let's dim the lights a little bit. I see some of you are pretty tired to begin with. This should help. All right, so sequences. First, what is a sequence? Make that a little bit bigger. So a sequence is a function, all right? Remember, you don't have to copy everything I put up here down. The main idea here is that a sequence is a function. Well, we've seen in the past, right? When we've dealt with functions, this was kind of the classic picture we had for a function, right? F. And then over here was the domain, and over here is the range, right? The things that we've plugged into the function, right, throughout college algebra, pre-cal, Cal 1, even most of this class, the numbers that are plugged in here are usually real numbers, right? You can plug in different, whatever you can think of, try and plug it into the function. And then our output is always a real number. So if I give you something like this, f of x equals x squared, then when we go and take a look at the graph of this, it looks like this, right? And that picture represents what would happen if you start plugging different values in here, right? Plug 0 in, you get 0. Plug 1 in, you get 1. Plug 2, you get 4, right? But you can also plug in 1/2. You can plug in 0.2. You can plug in pi, any number you want, right? So the input, right? The input is any number you want. That's a function. Well, any number that works, right? Some functions can't handle the numbers, like 1 over x. You can't plug in 0, right? But other than that, you can plug in any other number you can think of. A sequence is a function that basically restricts this domain to just the natural numbers. So a sequence does this. Takes just natural numbers. It's actually, the double struck is on there, sorry. Double struck, I always double strike that one. But so you know how we have a double struck? This is called a double struck capital R, because it's struck twice here. That represents the real numbers. A double struck N represents the natural numbers. So the natural numbers is the set of numbers 1, 2, 3, forever. Okay? That means your function only takes inputs that are positive whole numbers. So you can't plug in 1/2 into a sequence. You can't plug in pi to a sequence. You can't plug in the square root of 2. You can only plug natural numbers in. Which means if we graph it, so imagine that I have a function that is defined this way. Let me call it f for now. If I said f, and normally we put f of x, right, equals x squared. With sequences, because we're using natural numbers, we usually write f of n equals, and then here's the formula, n squared. These are very similar, right? They look like they do the exact same thing. The big difference is in the picture. What's the picture of this going to look like? Yeah?
It's going to look like the positive x side.
It's going to be this. Is it going to be everything, the whole curve?
No, it's only going to be like dots, dots.
Dots, right? So it's going to look like, at 1, you have a dot at 1. At 2, you have a dot here at 4, right? At 3, you have a dot at 9. And so it's just a bunch of dots, right? That's all it is. It's not a smooth, continuous curve. It is just a sequence of points, right? So that's what a sequence is. The domain of a sequence is all natural numbers. The outputs can be any real number. So what comes out does not have to be a whole number. It can be anything you want. I mean, it can be anything can come out. In this particular example, the only things that come out are positive integers. But it's possible to get fractions out. I'll give you an example of a sequence that would give you, how about this one? F of n equals 1 over n. Okay? What are the outputs of this thing? So you start by plugging in 1. What happens when I plug in 1 there? 1. Plug in 2? A half. Plug in 3? 1/3. 1/4. See, so you're getting fractions out. The thing that makes a sequence is the things that are being plugged in. All right? Okay. Notation for a sequence. Instead of using, I'm going to make this just a little bigger. Traditionally, right, we use f of x. Go walk around, do some push-ups, do something. Get to chapter 8, you just crash and burn the rest of the way. Got to pay attention. Okay, normally we use f of x, right? We're not going to do that anymore. Okay, we're not going to use this notation. The notation we use for sequence is a sub n. It's different, it's very different. And it's so we don't confuse it with a function. As soon as you write like f of something, people think, oh, I can plug in any number I want. By writing a sub n, what we're doing is we're stressing to you that we're looking at a sequence. All right? So I'm going to give you this example here. That one right there is written a sub n equals n squared. That's the way that you would write that function. Or I should say now, that sequence. What it is instead of using like f of x, right? We don't want to use that. We could use f of n, but we say no, we're not going to call it f, we're going to call it a, and we're not going to use parentheses, we're going to subscript the input. So this is like the name of the sequence is a, and the subscript is the input number. The nice thing about this notation is that if we use this notation, then we can write out a list of just the outputs. So your first number in this list is what you get when you plug 1 into the sequence. The second number in this list is what you get when you plug in 2, 3, 4, and so on and so forth. So like for this sequence right here, if I were to write this sequence out, I would write it this way. What do I get when I plug in 1? 1, comma. What do I get when I plug in 2? 4, comma. What do I get when I plug in 3? 9, comma. And then I keep going, right? 4, 16. That right there is the formula for the sequence, and this is the sequence actually written out. When you look at that written out, you have to understand that this is a sub 1, right? This is what I get when I plug in 1. This is a sub 2. This is what I get when I plug in 2, right? This third one is a sub 3. This is what I get when I plug in 3. So writing it this way, we're just listing the outputs, right? That's all it is, just the outputs. My mouse. How about this one? May as well do it while I've got it here. How about this one? A sub n equals 1 over n. If I write that, it would be what? 1, 1/2, 1/3, 1/4, dot, 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 right? Keeps going. When I do dot, 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 usually in math, 3 dots represents that it goes forever. 4 dots, 5 dots is fine, but like most of the time we use 3 dots. I get crazy. Sometimes I do 7. It just depends. But 3 dots is enough for you to imply that that goes forever. All right? Now, we have finite sequences and infinite sequences. An infinite sequence, you just write a sub n. And it's implied, it is implied here that the n's you're going to plug in are going to be 1, 2, 3, 4, and you go forever. It's implied. Now, if you want to, you can express that explicitly that you want it to go forever. So you can write it a sub n, put the whole thing in in braces, and then go n equals 1 to infinity. I'll show you. Let's do this one right here. If I wrote this, n squared, n equals 1 to infinity, that would mean 1, 4, 9, 16, dot, dot, dot forever. All right? Here's my sequence formula, and I'm explicitly stating where I want n to start and where I want n to stop. Look at that compared to a finite sequence. Here I can control where I start and stop. So if I wrote this, n squared, n equals 1 to, let's say, 5, then this sequence would start 1, 4, 9, 16, 25, stop. This is a finite list of numbers. This is an infinite list of numbers, right? What about this? I can control where to start. If I want, I can start at 4 and stop at 7. What would this be? 16, 25, 36, 49, right? That would be a finite sequence. But I've started it at a different place, at 4 and stopped at 7. Question? Oh, sorry. You see, I see what you're looking at. Sorry, that 2 goes up here. Okay, yes?
So we can write the formula for the sequence as a sub n or even in braces a sub n?
Yes, you can do it either way. Yep. If you just write it this way, where you're implying it starts at 1 and goes forever. If you write it this way, you're implying it starts at 1 and goes forever. If you write it this way, now you're telling me for sure it starts at 1 and goes forever. Now, if you just write the sequence, you can give me a restriction on n. You can tell me, okay, for n's, between 2 numbers or whatever, or this notation, which is usually the one we would use, where you're explicitly saying, hey, start here, stop here. All right. So far, okay? Now's the fun part. This is where we start to figure out how your brain works. I'm going to put the sequence up, and you're going to give me the formula. So I'm going to give you the list, and you're going to give me that. All right? This is a fundamental idea in this class. If you struggle with this, it's going to be bumpy the rest of the way. All right? So common sequences. You know what? shit. Let's do this. I don't want you to see them. I'm going to put the sequence up, and then you're going to tell me what the formulas are. And we're just going to go around the room, okay? Everybody's going to get called on. And these are going to start out easy and get harder. Well, not necessarily. Some of them are. Okay, so you ready? This is going to be fun. And you know what? I have this all in my notes here. Could just work out of this too. So I'm going to put the list up, and you're going to give me the result, all right? Here it is. So I want us here to find A sub n. Find the formula. All right, we'll take a volunteer. How about we do volunteers, and then when I run out of volunteers, then I'll start appointing people. I saw you, and then you put it down. You change your mind? Yeah? Not X. Yes, but not X. N. Yeah, N, right? So we're going to use N only. So this is the formula for this is A sub n equals N. Or if you want, you could have written it this way. N, like that, right? Because what do? You plug in 1, you get 1. You plug in 2, you get 2. You plug in 3, you get 3, right? Got it? Volunteer? Oh, and let me also tell you before you answer. You're not allowed to control the index. You can't tell me that this is this formula again, but starting at 5. I want the formula. I want just a formula. You want to still go? Okay, what do you got?
It's equal to n plus 4.
N plus 4, very good. All right. So do you all see that all this list is the same as this list? Except instead of starting at 1, we start at 5. So I needed to add 4 to this number, right, to get to here? And then instead of 2, I have 6, so I had to add 4, right? Instead of 3, I have 7, I add 4. Every one of these is just this list shifted by 4. So we put n plus 4. It should work, right? Check it. It's easy to check, right? Plug in 1, what do you get? 5. Plug in 2, 6, 3, right? Questions? All right. Good question? Yes? Yeah, so now I'm not going to use this notation much, but just to show you, you'd write n plus 4. That would be it. This is the one I'm going to use almost exclusively in here. All right, how about this one? Volunteers. But you can only volunteer once. Go ahead. N minus 11. What do y'all think? I think you're close. Will it work? N minus 11. What happens if you plug in 1? What do you get? Negative 10, right? So hold on. You're here, right? You're starting here. So N minus 12. Good. N minus 12. The thing that you should see is this. In all of these lists, do you agree that as you go from one number to the next, all you're doing is adding 1, adding 1, adding 1, right? So the change is 1 each time. Notice in all of these formulas, there's a 1 in front of the n, 1 in front of the n, 1 in front of the n. That's how much you're going to change by. The number next to the n, the 4, the negative 12, here it's what, plus nothing? That's kind of like a shifting where you're going to start from. So if you don't shift, then you're going to start at 1 and just count by ones. Here, you're going to count by ones, but you're going to start at, well, you're going to shift it by 4. So you're going to move everything over to the right 4, which means you're going to actually start at 5 when you plug in 1. Understand? So this one right here, n minus 12. Yeah? Okay, next one. The longer you wait to volunteer, the harder they're going to get. Go ahead. 2n. 2n. 2n, right? Hey, those are the even numbers, aren't they? Starting at 2. Those are the even numbers starting at 2. We're going to use this a lot, all right? We're going to use this a lot. Could someone else do this one? Could you give me the even numbers starting at 0? Who's got it? Go ahead. 2n minus 2. 2n minus 2, right? Because if you plug in 1, you get 2 minus 2 is 0. You plug in 2, you get 2 times 2 is 4, take away 2, gives you 2. And then you keep, see, the thing here is like the 1 was over there, right? This right here is how much you're jumping by. Plus 2, plus 2, plus 2, right? Same thing here, plus 2, plus 2. And then the number on the outside is where you're going to start from. Yeah? This one. Next volunteer. Go ahead. 2n minus 8. What do y'all think? Yes or no? 2n minus 8. Yeah, you can check it, right? Those are all increasing by 2 each time, right? Check it. 2 times 1, that gives you 2. Take away 8, you get negative 6. And then once you start there, it keeps going up. Yes?
Do you ever put n as the power?
Yes, you could.
And then I remember something from pre-cal where it was like an oscillation where one was negative and then the next one was positive and the next one was negative.
We're getting there. Mm-hmm. Okay, so these are all jumping by 2, right? One, 3, 5, 7. Those are odd numbers. Who wants that? No more volunteers? Go ahead, Ash. Sorry, Joey. 2n minus 1. What do y'all think? Are they jumping by 2 each time? Yes. Okay. But you need